All right, so today we're going to talk about a different but equivalent approach to quantum field theory called algebraic quantum field theory. I dislike this terminology. It's old. And what it is nothing but, I would like to call it local quantum field theory. All right. Now, we're going to see what happens. But let me just give you a high-level description. So far, we've built quantum field theory stressing the principles of locality, symmetry, and positivity of energy. We mentioned it in passing. And then causality came up, right? So those were the things that we built everything with. Now, in our discussion, the starting point of it was something we call the fundamental field. These were things that we decided they're going to be transforming under EREPs of the symmetry group that we had, right? That was the key idea underlying our approach to quantum field theory up until now, and actually the remainder of the semester. But I'm going to take a short break from that and give you an alternative picture. It's equivalent, but alternative picture. Okay. I also said in various points along the way that fields are not fundamental. Even though that was a starting point, I said, sorry, I didn't say fields are not fundamental. I said particles are not fundamental. So what you put in the Lagrangian, you might not see it, we might not see it this semester, but what you put in the Lagrangian, in your Hamiltonian, UV Hamiltonian, the degrees of freedom in the UV might look very different from the degrees of freedom in the infrared, right? We saw that explicitly in the case of a theory of phonons, right? A bunch of sites. So the question is, if you're an infrared observer, are these two equivalent? Is there a sense in which that the UV degrees of freedom are more fundamental or not? Is there such a thing as more fundamental degrees of freedom? So I'm going to make this very obvious as we go along. But what I want to say is that there is an ambiguity or arbitrariness in definition of a field. We're going to call it frame dependence, right? And the goal of algebraic approach is to pick a frame independent formulation of quantum field theory. Good. I'll make this with simple analogies and hopefully it will click. It should be pretty straightforward. But in this formulation, the fundamental objects are observable algebras. Good. Okay. Now I need you to be a little bit patient with me. Okay, sorry. Is that good what we're doing? We're going to talk about, first I'll tell you what dualities and frames are. And then we're going to talk about the formulation of quantum field theory or quantum mechanics. As a matter of fact, you'll see that is independent of the frame. Good. The fundamental object is going to be algebras. To do that, I have to first define for you guys what a quantum system is. Do you guys think you know what a quantum system is? Do you think you know we can define a quantum system? Okay. We're going to do that. Of course, the definition will not blow your mind when we're talking about finite dimensional Hilbert space systems, finite quantum systems. It's exactly what you know. But as we talk about infinite dimensional Hilbert spaces or infinite dimensional systems, you might think of harmonic oscillator as an example. And probably most of you think, oh, quantum field theory is also infinite dimensional. But not all infinities are created equal. Today's lecture, huge part of it, part of the problems we have with quantum field theory, in particular UV divergence and infrared divergences, the origin of it is that there are two types of infinities. Countable infinity, uncountable infinity. Okay? So what I'm going to do next is I'm going to give you a definition of quantum mechanics. What a quantum system is, it goes back to 1935 when von Neumann was trying to make sense of quantum mechanics. Of course, as a mathematician, he defined it in one shot for finite, infinite, whatever dimensional. He defined what a quantum system is, okay? So what is a quantum system? I'm going to talk about the Heisenberg picture. So whatever I say is a formal definition. have Heisenberg picture in mind. Okay? Whether it's equivalent to Schrodinger picture or not, we're not going to talk about for now. Okay? So what is a general quantum system? Let me just run an analogy. Take a qubit. Yeah, take a qubit. I want you what a qubit is. I want to define what a qubit system is. Well, it's what it is a set of observables. Right? When it comes to a qubit, what are the observables? Permutation 2 by 2 matrices. Right? Those are the observables. Okay, so that we those are the observables, right? Permutation 2 by 2 matrices. Examples. Identity, sigma x, sigma y, sigma z. Right? Now you already know that there is a sensible way to add these guys. There's a sensible definition for adding operators with complex coefficients. Right? So there's an addition operation. So first, relax this self-adjoining definition. You could just add them with complex coefficient. You could talk about sigma x plus I sigma y. What's that called? Sigma plus. Okay. So there's an addition operation with complex numbers. You could multiply one of these guys by complex number. Right? You could multiply these guys. So now this is a general operator. You could multiply two of these guys. The order matters, but the multiplication is associative. I don't even need to say these words. You know that, right? Okay, so you could multiply them. You could add them. What other operations do you have? You have one more operation. I already used it in my words. There's a notion of a star, dagger. When a mathematician says star, the physicist hears dagger, right? So if you take to every operator A, there's a unique operator defined as a dagger, such that a dagger is A. Right? That's all that there is to quantum mechanics. What's a mathematical object where you have, think of these as this, think of this, these are, think of these as vectors. So this is a complex vector space. And algebra in mathematics is a complex vector space, linear vector space, right? Well, it doesn't have to be complex. It's a linear vector space. It has an addition operation. Addition operation, of course, is vector space. There's a multiplication operation, right? And it's closed under both. You add a number of these guys, multiply a number of these guys, you're still talking about the same object. Still in your set. Closedness is where things get funky when you talk about infinite dimensional systems. In 5 dimensions, it's pretty obvious, right? So it is an algebra with addition, multiplication. There is a dagger. Such a thing is called a C-star algebra. That's a pretty simple thing. C-star algebra. Okay. So at this level, it seems appropriate to define a quantum system as a C-star algebra. That's not what we're going to do. There's a subtlety that comes up in infinite dimensions. Okay. Everybody good with me? Okay, so this is what a quantum system is. Von Neumann, 1935, told us a general quantum system in finite dimensions is a C-star algebra.
And so, like, this is just a definition for C-star.
Yeah, it's an algebra. It's an algebra. It's closed under, there are two operations, addition and subtraction. They act the way you expect addition and multiplications to act. And it's closed under them. There's a star, which is even formally, you don't even need an identity. There's a canonical way of adding. Okay. Very good. Now, this is, ignore this comment. Put this aside because this, I just moved this slide, move them around. Okay. In this case, I gave you a representation of the algebra. Right? That's what they did. I give you a representation. When I say sigma x, you think of, oh, matrices 1, 1, this way, blah, blah, blah. That's a representation. The algebra can exist independent of its representation, right? If you rotate these guys, you still have the algebra. As a matter of fact, it's not important how you generate the algebra. The algebra is the algebra. Complex 2x2 matrices, right? I don't need to tell you how to construct. I don't need to tell you that, oh, take C1 plus identity, C2 plus sigma x plus C3 sigma y plus C4 sigma z to say I have 2x2 matrices. I just say 2x2 matrices. How we generate the algebra is a frame, right? The quantum system is the algebra, right? So what is observable, or observables are a form in algebra, but I'm just gonna give you a recipe for how to construct them. That would be a frame. Like take these matrices I show you, multiply them with complex numbers, and that is an algebra. That's a recipe for getting the algebra. But it's a particular choice of recipe. For example, I gave an example of take unitary rotations of this. It's the same thing. It's a different frame. As a matter of fact, they don't even have to be like orthogonal or anything. I can give you all there are a bunch of matrices, just generate 2x2 matrices, right? So there is a notion of a frame hidden in the way we describe the system, a qubit often. And that is really the idea of, oh, where is, like what I picked to be, this is a spinner. What did I pick to be my sigma z? Is it this one, or is it this one, or is it this one? It's choice of coordinates. Good? Everyone's with me? There's another thing to realize. This is a very good example because I generated the algebra using a group. What's a group? These are U2 matrices, the identity. Right? This is a Lie group. I can also talk about the Lie algebra for the originals. These are exponentiation of you. Hopefully you can guess what that. I'm not gonna call. Okay. I can talk at the level of the Lie algebra. I can talk at the level of the Lie group. All of these are a representation. I'm giving you a representation. Sorry. I usually in physics we talk at the level of representation in a particular frame. Good? All right. So there's frame dependence. So we want to move to, so there's frame dependence and description of what a qubit is. Next step, let me describe frame dependence and harmonic oscillators. Good. So the simplest infinite dimensional system, and then you have in your mind, oh, quantum field theory, whatever the hell it is, it's just a collection of harmonic oscillators, at least free field theory. Good. So we're going to take the steps. A bunch of things happen. So what I'm going to do is I'm going to give you another way of thinking about the canonical commutation relations. Remember what that is, right? X hat and P hat. They generate a Lie algebra. What are the relations? These are X and P. They give you identity, X and identity, and P and identity commute. There are three generators for this Lie algebra. It's called the Heisenberg algebra. X and P give you identity, and X and an identity commutes to both of them. So it has a center. Good. So if you ask me, can I give you a representation? Here it is. These matrices satisfy these relations. This is a representation, perhaps unfamiliar to you guys, of the canonical commutation relations. I could have talked about the quantization of simple harmonic oscillator using these matrices and their exponentiation. When you multiply X and Y and Z's, what are the observables of simple harmonic oscillator? X and P. Add them with all sorts of things. Multiply them, right? X squared, P squared, XP plus PX. And if you just say observe operators, you don't say observables, just make all sorts of linear combinations. Right? Okay, you notice that in this analogy, X and P are the Lie algebra, guys. The same way that here we had the U2. Over here, what do you obtain? You have to exponentiate X and P, right? What are those operators? Here's what you get. This is, what is this? What's this? What is this guy? You know, recognize e to the power of ISP. Translation operator. What is this? It's a shift in momentum. This is the algebra they satisfy. If you want to derive this, use BCH, right? Just follows from commutation relations. CCR. Good. So here it is. This is the multiplication rule of the algebra for you. So based on what I told you, an alternative way of thinking about the elements of the of this algebra are just, what did I say? I said, oh, just take complex sums of the generators of the independent elements of the Lie group. Here you would take e to the power of ITX, e to the power of ISP, those guys, and add them up with all sorts of coefficients. Good. Those are observables. Notice that both of these, you already see the definition. This is a unitary group, representation of a Lie group, right? So is this one. You already see some sort of a fine line I'm walking. I'm sort of using a symmetry to define a quantum system. All right, are there any questions about this? CCR is canonical commutation relations. I'm intentionally avoiding talking about the car algebra anti-commutators. It's not more complicated, but I just don't want to confuse you guys for now. It requires one bit of mathematics, one extra bit of mathematics. Does anyone have a guess what it is? There's something called, we talked about Lie algebras and Lie groups. We talked about something math called graded Lie algebra and graded Lie group. It's just one extra complication, but let's not worry about that. All right, so everyone's with me? Okay, these are called Wild relations. This is describing an infinite dimensional system. All right. Now I'm going to use the word duality. This is the only use of the word duality we know in physics. Okay, I did not say that in recording. Maybe someone comes up with a weird tangent duality, but this is what usually means. What is duality? Duality is frame dependence. What was duality in a qubit? What I picked to be my x and y and z. How I generate my algebra. My algebra is the algebra, right? Sorry, that's not duality. That's frame. That's a frame. The fact that two different frames could be equivalent, that's a duality. If I describe my qubit using one frame, it might give me some results. And then someone talks about another quantum system that they've generated using a different frame. And then I have this aha moment that up to unitary, they're the same frames, and they say, that's a duality. There are two different ways or frames that generate the same algebra. Right? Okay. So what is the frame dependence? And simple harmonic oscillator. What are your fundamental fields, X and P? Right? That's what you take as the onset and multiply these guys to generate all sorts of complicated things. X and P. Are they really fundamental? Let's see. So what do they satisfy? They satisfy the commutation relation NA dagger is equal to 1. You could immediately do a Bogoliubov transformation, which is define B and B dagger. Well, B dagger is defined naturally by introducing some numbers, U and V, complex numbers. And when you calculate the commutation relation of B and B dagger, it becomes proportional to NA dagger up to that constant. Now, if I choose my U and V such that U squared is equal to V squared, B and B dagger are an equivalently good frame to describe the same harmonic oscillator. These are called linear Bogoliubov transformations. Right? Yeah.
I think when you first define B dagger, you're missing an A dagger.
Oh, sorry. Thank you. This is what happens when. Yeah. Thank you. There are hats also all over the place. Good. Sorry? Yeah, thank you. If by find a number of moves, you can go from my equation to correct equation. It takes an infinite number of moves. No problem. No problem. All right. So there is some frame dependence. This exists in classical physics. Do you recognize this in classical physics? This is already a thing in classical. What is the X and P space? Phase space. You're picking a basis for phase space. What those guys are, they're like rotations in the phase space. What I used to call X and the orthogonal P, let's just rotate it and look at it this way. Physics is the same. Hamilton, Jacobi equations don't give a damn. It's just a flow. Right? So it's the same business here. That is what a frame is, and that's what, yeah, if you talk, the point is that the fundamental objects that we've proved, fields that we've been holding on as if like they are totally sacred, are nothing but the choice of frame to generate the algebra. It's a recipe for generating the algebra, right? The frame independent way of talking about it is to take one step further, become a wear your mathematician hat and say, here's my algebra of observables. Right? The algebra of observables is the algebra of observables. That's why we say the quantum system is a C-star algebra and not that A and A dagger, B and B dagger. They're equivalently describing the same system. The qubit is not sigma X, sigma Y, sigma Z. It's an algebra of 2x2 complex matrices. Good? By the way, if you want to know what this algebra is called, it's a von Neumann algebra that's called one infinity. All right, I haven't told you what the von Neumann algebra is, but I will tell you that in a second. All right, any questions here? So that's what duality is. A and B are two different duality frames to describe simple harmonic oscillator. Do you recognize that condition? U squared minus E squared. Is that a rotation? I like it's not a rotation. What is it? Do you know what it is? No, it's very close. It's not S. So the groups that you recognize are so far. Remember SOD. You recognize what else do you recognize? You know SUD, right? You recognize SO E comma 1. So there are boost rotations, some sort of complex effect version. This is we're talking about SP. So how are these defined? As transformations that preserve some metric. Preserves this guy. There's a name, this is called the symplectic form. It's the volume form on the phase space. And formally, we say all the transformations that preserve the symplectic form or the volume on the phase space are symplectic dimorphism. So that's just like being a mathematician. But what it is you recognize this, right? All rewritings of the degrees of freedom of physics, if they preserve the volume of the phase space, should not matter, right? Because the only thing that appears in Hamilton's flow equations are the volume. All right, so that's what it is. Of course, as the generalization to n degrees of freedom is instant. That's why I put D already in there, but we'll get there. Okay, let me repeat this. These A and B's, they generate the same groups and algebras, right? But by choosing a particular, not particle, particular duality frame, we're choosing a preferred basis for generating the algebra of the observables. Physics is frame independent, but as usual, we describe it using the frame. This is a big distinction between mathematicians and physicists. We love coordinates, but we also know coordinates are arbitrary, right? And mathematicians love to describe things in coordinate independent ways, right? This is, you could think of this as some sort of coordinates on the phase space, as I said. Okay, this is, I don't know if you already have, okay. The analogy with phase space is so direct. We're going to talk about that later. Maybe you've seen it already, but anyway. So in canonical quantization, and as a matter of fact, in covariant quantization, quantum field theory, but you haven't seen that yet, we choose a basis. The x and p's are the phi and p hats, phi hat and p hats, right? That's a basis. In the algebraic approach, we talk about the algebra of observables in a frame independent way. Okay. Good. There's a lot of physics in the choice of frame. Where is it? Can you tell me? When I say a Q-dit, that means the algebra of D by D matrices. The physics starts when you talk about comparing things, right? How frames evolve in time. This comes at the cost of just like taking a lot of soul out of the system. If you want to define what a quantum system is, you just say a Q-dit is this thing. But there's a lot of physics we do with Q-dits, and that requires fixing the basis, right? There are a gazillion different Hamiltonians I can write down for a D-level system, quantum system. This just steps away from that, because to define a quantum system, I don't need to talk about Hamiltonians, right? All right, good, very good. But point is that algebraic way of talking about stuff is frame independent. What you should expect here is once we reformulate everything in an algebraic language, it's going to be absurdly general. It's so general that it's extremely general, but then we'll lose our calculational power. That should be obvious, right? What's good about picking a frame is that there's a recipe. There's a recipe to generate things, but there's a recipe for calculation. There's Feynman diagrams. There are all sorts of things you could do. But when you take a step farther and talk algebras, all that you can see are some very general math statements. It's good to get closure, like about what you were talking about being rigorous, but calculation, you're very limited. All right, any questions? I have to speed up.
I make one conclusion here.
Yeah.
When you say duality, it means two different frames can generate the same algebra.
Yeah.
So here, AA dagger and BB dagger, they are not the same. The commutation are not the same.
Well, I mean the transformations, right? No, they generate the same algebra. So they're dual pictures. Yeah. The generators are different, but the algebra is the same. They're different representations of the same algebra. Right? Good. Sorry, does that answer it? Or if it's not clear later, ask. Okay. There's one more thing that I want to say. So this might not have been clear. I'm going to use the word vacuum for the lack of a better term, but well, actually because of the analogy. But as a physicist, you should be open-minded about the use of the word vacuum. We'll see. So the choice of, so that was Heisenberg picture. Everything I said was Heisenberg picture. What about Schrödinger picture? What, if you recall, the story gets interesting with harmonic oscillator. There's more to harmonic oscillator than in a diagram. In harmonic oscillator, there's a choice of a vacuum. It's the same way that we can talk formally about the Hilbert space. We could talk about a frame to generate the Hilbert space. What is that frame that we talked about? Vacuum is the state killed by A. Then the Hilbert space is generated by the action of a dagger repeatedly on this. Right? That's again a frame. In another frame, when I define B, my vacuum is not the previous vacuum. It's this thing that has so the initial vacuum was a state with no A-type excitation, whatever the hell that means. The second one is another state, but it had no B type excitations, but by calculating with B dagger and all sorts of powers of it, I generate the same vector space, Hilbert space, right? If the Hilbert spaces I obtain are unitarily equivalent, this was a duality thing, right? The unitaries are the only things that matter. Unitary in physics, by now you should know this. The choice of frame is all about unitary rotations, right? X is here, Y is here, Z is here. Let's rotate them by unitary. Why is that actually, do you know? Because unitaries don't change multiplications. When you have an algebra, or if you have commutations, the commutation relations are not unchanged on the unitaries, or multiplication of group elements are unchanged on the unitaries, right? All right, so those are the redundancy of descriptions. What I just told you was a physicist talking. That's more subtle than that. All right, so the choice of vacuum is a choice we always make in physics. And I just wanted to make it very manifest that it is intimately tied to the frame we generated algebra with, right? So far, everything is good. Now, when we talk about, okay, so good, we're good. I should ask, not say it. Good. Here comes an important, extremely important result in quantum mechanics that most of the time people neglect because it's considered history, right? And then we're sloppy with like a lot of math. So it's called the von Neumann uniqueness theorem. It says the following. So what let me give you a context. The question is this. If I take the choice of X and P that give me NA dagger, or another choice which gives me B and B dagger, are the resulting Hilbert spaces unitarily equivalent? Right? That's the question. Von Neumann uniqueness theorem says if you're talking about the algebra of A and A dagger, it's a true statement. Okay? It says, imagine besides, so let me write the algebra on the board first. So what did we have? It's nice, you could formulate the level of the algebra. We have this relation, right? Oh, I'm not gonna write the rest. I might be wrong about the sign. This is the relation, right? This is what you recognize from the simple harmonic oscillator. Now I say somebody comes to you and says, I have a Hilbert space at US, one parameter family of US, VT, such that they satisfy these relations. The question is it true that every time you have such a setup, U and V are unitary rotation distance? If it is, we're good. That's what von Neumann proved. He proved that this is actually a description of the group or algebra that's frame independent. There is some U, some V, these are unitary flows that satisfy these relations, right? This just gives you an idea of how you could describe things in frame independent. But von Neumann proved that if there exists such a pair, there exists a unitary such that U after unitary rotation is e to the power of itx and V after unitary rotation is this, right? And they act the way you would think. The statement is that the vacuum is also unitary rotation, right? All right. All good? It's an incredibly important result that people take for granted. We'll see that how its failure is going to give us help. Good. All right. The idea is this. What happens if you have a bunch of oscillators? So remember the algebra I wrote before about X and P? I gave you these matrix representation of them. Here's what, so let's say I have an N, capital N, finite number of harmonic oscillators. Here's your algebra, Z's identity, but it doesn't matter what it is, right? Because I'm gonna represent it this way. This is Z. These vectors are EI is just like has an 1 on the ith component, and they satisfy this algebra. So this is a representation. This is a how many dimensional representation? Well, you can count. I cannot. It's a representation of this algebra. Stone-von Neumann theorem is a generalization of what we just said. These are CCR relations for n modes. It says for a finite number of CCR modes, the representation is unique up to unitary and the Hilbert space. That just means this story generalizes to finite number of harmonic oscillators. That's good. And that's why you never learn about this unless you take a course on many-body quantum systems. So that's good. Good. The key word here is finite. Even back then, von Neumann knew how important it is that this is finite, and the moment that is infinite, hell breaks loose. It gets really bad. As you can recall, that's the case of quantum field. Right? Whether it's an infrared divergence or UV divergence, one way or another, it's always about the number of allowed momentum modes, because in quantum field theory, for each momentum mode, right, we had in canonical quantization, spatial momentum mode, we had the creation annihilation curve. UV divergence has to do with the fact that the momenta could be arbitrarily large. IR divergence has to do with the fact that they could be arbitrarily small between 0 and a number. You could just stack many of them, right? IR divergence is actually kind of worse from this perspective, but it's not. Oh, okay. Good. So there's a problem when you have infinite number of harmonic oscillators. The theorem fails, not because we can't prove something better. It's just incorrect. It means that when you define quantum field theory with a bunch of AKs, where does this AK come from? It comes from, recall what our definition was. It was phi of k, phi k plus aggregate. Something there are omega k's all over the place, right? Square root omega k up and down. But AK was constructed out of these guys. So it refers to a frame. And your vacuum refers to a frame. So the Fock space we defined was defined in a particular frame. How do you define the Hilbert space? The same way that we did before, by saying, here's my vacuum, now act with a bunch of AK daggers. Here comes the first complication. You can't act with an arbitrary number of them, right? You have to make sure your state remains square interpretable. That's what the Hilbert space is, right? So you can't write whatever the hell you want, like this state is not square interpretable, right? So this is not allowed in your Hilbert space. But you could get to things like this. If you allow me to act with arbitrary number, infinite number of AK daggers, I can generate all sorts of stuff, right? So there are some constraints. This describes to you a Hilbert space, as you recognize, as a vacuum of a simple quantum field theory, right? But importantly, it's not unitarily equivalent to arbitrary other Hilbert spaces, you could have other states that you could have defined. Do you have an example? Let me see if you can come up with. What happens when you act with the UK? You add an excitation of finite energy, right? What is the energy? M squared plus K squared, right? So the question is, of course, if the two states are different by a finite number of particles, they're in the same Hilbert space. But what if it takes an infinite amount of energy to go from one to the other one? That you should not expect to be the same Hilbert space. I mean, generic was not. Give me an example from physics. Like, I know what a vacuum of quantum field theory is in free field theory. Give me an example of a state that has infinite energy more than the vacuum, and we talk about this all the time. What state do you recognize? Do you know? Sorry? Oh, no, it's simple, right? Just let's stick with bosons. Free, coordinate state, unless you tell me more, you have to say which coordinate state. Some of them are, some of them are not. But okay, here. The keyword I told you to build intuition with infinite amount of energy. What states do you recognize that have infinite amount of energy more than the vacuum? We talk a lot about it all the time. Almost, give me an example of state. I'm pretty sure it's like that. Remember that space is infinite. So if I put energy density anywhere, finite amount of energy density, I say, well, vacuum, it looks like vacuum everywhere. Now I'm gonna say, oh, I have finite but arbitrary temperature. That adds energy density here, right? There's a non-zero amount of particles, expectation value at this point, but the space is infinite. Right? It takes an infinite amount of energy to go from vacuum of quantum field theory to quantum field theory at finite. They are two different representations that are inequivalent. The algebras are different. We don't have the luxury of one Neumann theorem. We are talking about two quantum systems that are different.
What system is vacuum of its own?
Well, very good. How do I define that? So, can anyone actually, based on what I told you, you should be able to tell that. This is a good. What's the? Can you define? Can anyone define what a simple harmonic oscillator is in the language of sorry, finite temperature simple harmonic oscillator is in the language of any dagger?
It's like E2 minus beta over T times.
Very good, very good. E minus beta. Good. Which is number operator, right?
Yeah, and
Okay.
then times the density.
All right. So let me just describe it first. It's not a pure state.
Yeah.
Okay. So I have to write something mixed, right? Let me write down the purification of it. What's called the thermal field level, right? I have creation on the left and annihilation on creation and annihilation. Okay, sorry. Let me not. I'm going on a tangent, but there's a way of writing. There's a way of writing in terms of creation and annihilation operator. That could be a great homework problem. Good. And there's a relation like that you write down. Okay. And these are not equivalent representations. The Hilbert spaces equivalent means up to unitary. They're not up to it, like when we say they're equivalent, it means that, oh, I could have, even though I started in this state, it's okay, I still have the other state you have in mind, because I'm gonna just like apply a bunch of transformation, my Hilbert space, a unitary rotation and get there. The point is, there exists no unitary rotation that will heat up the vacuum of quantum field theory to find. There exists such a thing. They're mathematicians say they're disjoint representations. That's what it means. There are no unitary voices. All right, I'm gonna, in the interest of time, if I have time, I come back and comment on this. But in the interest of time, I'm just gonna skip this. Oh, actually, let me just say a few words. It is think of this as an infinite lattice. Right? At each site, you have an AK, right? Then K is like a site on the lattice. The phenomenon we're talking about is not specific to QFT. It's also true in the thermodynamic limit of lattice systems. Good. So there are all sorts of, this is, as a physicist, you might have heard this word, different vacua, right? That comes up only in the strict thermodynamic limit. Either thermodynamic limit means infinite entropy or continuum, both of infinite entropy, right? If you have finite entropy, there's always von Neumann uniqueness theorem tells you that you don't need to specify for me a state, a vacuum, to define the quantum system. So what did we learn? We learned that when we're talking about these infinite dimensional system, to describe a quantum system is insufficient to tell you the C-star algebra. I have to give you a vacuum, right? So a quantum system in full generality is a C-star algebra with a choice of vacuum. There's a tiny bit more to turn that into what's called the von Neumann algebra, right? But the von Neumann algebra is always a C-star algebra. It is a C-star algebra with a choice of vacuum. Good. So basically, this is what von Neumann said. Hopefully, he didn't call it von Neumann algebra. The quantum system, a general quantum system, is a von Neumann algebra. It's a C-star algebra with a choice of vacuum. There's one extra condition. It's just closedness. That I'll tell you. I'll define. Actually, let me give you an example. Very good. I can give you a definition right now. The Hilbert space of harmonic oscillator is H, right? It's a unique infinite dimensional countable Hilbert space. The algebra of observables of that is called B of H. These are all the observables of simple harmonic oscillator. A von Neumann algebra is any star closed subalgebra of B of H. This is just to tell you how, as a physicist, what horrible mistakes you might be thinking and what I'm making by thinking all infinities are created equal. It means that every quantum system could sit inside the Hilbert space of simple harmonic oscillator. A single simple harmonic oscillator has enough states in it, this is infinities, right? That to describe quantum field theory with this continuum of spectrum, blah, blah, blah. Not so as a physicist, to a mathematician, that's a undergrad fact. But to a physicist, these are important. Good? All right. So what am I gonna do? All right, I said these, all of these. Yeah, QFT is a set of observable. So quantum, okay, sorry. So quantum field theory, or I would say quantum mechanics, is a set of observables, an algebra. It's going to be a von Neumann algebra. It comes with a choice of state. It's called vacuum, right? How is the Hilbert space defined? Based on what I've told you, you know. It's a recipe. What do you need the choice of state? It's a recipe for generating the Hilbert space. You say, take this state and act with it, on it, with my operators. You get new vectors. And keep doing that, right? And then what do you say in the simple harmonic oscillator? You say score integrable, right? Just, you have some sort of finiteness condition. You do this. You say, take your vacuum, take the algebra of observables, these are all the operators, you get a vector, take the closure of it. It's a limit. You include in the limits all the things that are fine. Have a score integral. This is the Hilbert space. All right. Very good. Any questions? So this is all, everything I said had no, in a sense, no QFT in it. It's just like quantum mechanics. From now on, in the remaining time, we're going to talk about quantum fields. So algebraic approach to QFT, which is a misnomer, is basically quantum field theory described in a frame-independent way, right? There's no contradiction between these. Some people think that, oh, people ask, are they equivalent? I think this is a silly statement. Are they equivalent or not? This description is a description of quantum field theory where we're gonna just do things only, all the things that are frame independent. So in the action formulation, or what is called Lagrangian approach to quantum field theory, this is this course and the next course, we're talking about the fundamental object that are the fields, phi A of x. That's how we start, right? But, and then there's an action, S of phi A. The point over there was that we're talking about, so the objects are fundamentally phi A's. What we're gonna say is that we're not gonna care about phi A anymore. We're gonna use, first I'm gonna use phi A to define an algebra for you. And I'm gonna say stick to the algebra and let go of phi A. Good? It's gonna come at a cost. But locality, what do we do with locality? When I had phi A, I implemented the locality principle in the locality of the action principle, right? I can't possibly let go of locality. If I let go of locality, I don't have any quantum field theory, right? So I need to reformulate all the, what are the properties that I had? I had locality, I had symmetry, right? I had positivity of energy, causality. I have to reformulate all of that in the language of algebra. That's what we're going to do in the remaining time. Okay? And nowhere in there, I'm allowed to use the word phi and pi. But before doing that, I'm first going to use phi and pi, build for you the algebras. That's analogous to going from x and p to these unitary things, right? The while algebra. Once I define the algebra and say, aha, stick to the algebra, forget how it's written. All right. So take free field theory. Analogous to x and p, your operators that you were talking about are these guys. Are these observables? They're surely self-adjoint, you would think. Are they observables? Yes, okay. Any other guesses? So, all right, if it's an observable, see the next principle, right? You should be able to use this principle. We define vacuum. I should be able to act with phi of x on this and get a new vector in the Hilbert space because I'm going to define the Hilbert space this way, right? Is this kosher? Oh, come on.
Yeah, it's like the ladder operators are defined using phi.
It is certainly a vector. What's its norm? One? No, tell me how to calculate it. All right. What is this? Oh my God. All right. Look at whatever equation you've ever discussed, like 2-point functions diverge at the point sit on top of each other. Okay? Must be. Is that an unfamiliar statement? What is this? Just go back to the calculations we've done before. This is divergent. This is awfully divergent. This is the UV divergence of quantum fields we were talking about. This is precisely the UV divergence of quantum fields. This is awfully divergent. You don't believe me? Do a calculation. But let me just do a calculation here for you. Take what you know, massive free fields. At very, very short distances, mass is irrelevant. Right? Is that clear? Because mass has length scale, and I'm going to take these guys. I'm going to take this to be x plus epsilon and take the epsilon going to 0. All right, mass is irrelevant. Mass drops out. What's the dimension? Well, actually, I don't even need to do that. What's the action? Minus half del mu squared. What's the dimensionality of the field phi? Minus 2 over 2, d is space time. Okay, actually, my notation here is space. So d minus 1 over 1, right? So this object is fixed pretty much by dimensional analysis. What is it? Because I said mass is irrelevant. You don't have any other parameters in your system. This is x plus epsilon minus x. Let's say there are space like separated. The power of d minus. We can see that it blows up awfully. It's divergence, how horribly divergent. And the dimensionality of the divergence is precisely what you expect from the UV divergence in quantum field. If you don't believe me, do the calculation by Fourier transform. So this is not okay. It's not an observable. Well, to make an observables, what we're gonna do is we're gonna take functions. So I'm gonna do first similar to canonical quantization, a non-covariant picture. I'm gonna treat space and time separate, right? That's why I'm talking about these operators, right? So let's do this. Let's take a constant time slice, right? Yeah, this is space directions. And let's take a function, a smooth enough function in space, f, and integrate phi of x with respect to that. Define an operator phi hat of f. Similarly for pi. If you look at what that is, it's just, this is, if after Fourier transform, phi f is like f star, f tilde, this is this Fourier transform. Phi of f is this object. Right? Let's calculate. So now the question is, I just looked at the more general. So this phi of x would be in this notation, phi of delta x. Right? No? What is phi of x? Integral over d of x, f of x, phi of x. I put delta of x minus x naught here. What do I get? Right? So what has happened? The issue is this. We define phi of f, and this is not quite a nice function. It's actually not, it's a generalized thing. It's a distribution. These guys are going to become, for nice enough functions, I'm going to show you in a second. They're going to be observables, right? This is a limit of it which is not kosher, and what this is a distribution valued operator. There's another name for it. So a field is a distribution valued operator because we have things like this. So let's take this guy and see whether when it acts on the vacuum, let's act with it on the vacuum, and it's going to generate a vector. Let's see if it has finite norm. That's all that matters, right? All right, so let's do the calculation. You can do the calculation, and you find this. When you look at the norm of this becomes integral of dp, of course, the covariant measure. I'm not going to write it again. You remember, right? Finally, somebody says something. Yes. Down shell omegas, right? Good. So it's an integral over all momenta, and if this function for very, very large momenta falls off fast, this is fine. What do you learn? You learn that if you pick a function, so this Dirac delta function was like this, pick a function that's a little bit smooth. That will regulate the UV divergences. Right? Because this guy is like an extreme level limit where what's the Fourier transform on Dirac delta? Constant. All modes contribute equally. That's bad. You want to suppress the UV. When you suppress the UV, they look more and more like this, right? Because there's a Gaussian approximation to a Dirac delta. What's the Fourier transform of Gaussian? Gaussian. So you're exponentially suppressing the UV, right? And those are good. All right, so that's what observables are. Very good. These guys, let's see if they generate something like a Lie algebra. Let's calculate the commutator. It's IH bar integral of dd of x, f of x, g of x. Yeah, that looks like a generalization of Lie algebras where now your generators are labeled by continuous functions. For the question of infinite dimensional Lie groups, Lie algebras. In a silly way, this is an example of it. I don't want to go down that path. Right? These are the analogs of X and P operators. They're unbounded operators, the same way that X and P are. Good? This is the Lie algebra generators. If I want to generate the Lie group, what do? I exponentiate these guys. Here's exponentiation, here's exponentiation. What is the multiplication rule for the Lie group? You just follow your nose, do the calculation, Baker, Hausdorff, Campbell, U of F, V of G. Oh, sorry. That's bad. This is V of G, U of F. I'm not used to covariant. I'm used to covariant formulation. This is what it is. And it's called the Weil algebra, Weil group. Because the previous one was called Weil group. Right? They're all bounded operators. Why are they bounded? There are unitaries. Unitary is bounded, right? What's the spectrum of a unitary operator? That whole. Oops. An operator is bounded if only F all psi. So an operator A is bounded. Actually, psi and phi in Hilbert space. I can talk at the level of the Lie algebras using phi's and pi's, or I can talk about at the level of the Lie group using u's and v's. But now I define for you the Lie group, and this defines for you an algebra. We'll see that in a little bit. This is the algebra of quantum field theory. Now I don't need to ever say the word phi and pi again. I define the algebra in terms of functions that live on the manifold. Okay, let's wait until this clicks. Are there any questions? I still have quite a lot to cover, but
review a representation of this algebra, then we get to the
every representation of this algebra is a quantum field theory. They're not materially equivalent. So it's not like you do one representation, you've done it all. No. Usually the way we describe it is using these operators and we say a choice of vacuum. That fixes for you everything, right? Because the Hilbert space is erased. The operators acting on it. That's why in quantum field theory, it's insufficient to tell me free scalar field. You have to tell me which vacuum. Is it vacuum? Is it thermal state? They're not equivalent. All right, any questions? Something. All right, and where we're gonna go from here, I'm gonna try to push it and cover the whole thing. There are two things I want to do. First, I want to define abstractly for you. I'm just going to talk algebras and write the postulates of quantum field theory, right? Or actually, as a matter of fact, what is called local quantum mechanics, local quantum system, which is, I'll have to tell you a notion of locality, define for a notion of locality. I have to define for you a notion of symmetry, like symmetries and stuff, and positivity of energy, causality, all of that. All right. So those are actually all that there is. I just told you, right? I'm going to do that first in the language of algebras that live on a constant time slice. I'm going to do that first. Next, I'm gonna take an extra step and write it covariant. Because there is still an arbitrariness in this algebra, which is I pick the Lorentz frame. Right? Ideally, I would like to describe it without even making that choice. We're gonna do that in a second. Any questions? That's what we're gonna do. Is it clear where we're going with this? All right. So, what is the fundamental thing we talked about? Of course, I have to use the geometry of space-time. And I'm doing similar to canonical quantization. So I pick a Lorentz frame. I pick a constant time slice. Now I can talk about this. To every region of space R, I'm going to associate a von Neumann algebra. For now, let's just say it's a seesaw algebra. We'll see von Neumann next time. Right? If you want to know what they are in this language, they are generated by phi of x and pi of g's when f and g are supported only inside the region. Right? When I multiply those guys, I still have functions that live inside that region. I only use the data of the region. Good? Importantly, I'll never need to talk about points. I'm going to talk about open sets. I didn't say that. Well, for this class, I didn't say that. All right. Regions, false. Is that clear? So these are the fundamental objects. I don't care you represent them using phi and pi's. If you do another thing, it's the same algebra. Let me say one thing to tell you how absurd what we've done is, in a sense. If I look at the if I look at the algebra of R for a ball-shaped region, I'll say this later. I'll say this later because this is not covariant. I have to make this statement covariant. All right, good. So I'm gonna do the postulates. So what is local quantum field theory in canonical quantization language? To every region, right, of a constant time slice, I associate an algebra. So it's a map from regions to von Neumann algebras that respects inclusions. If a region R1, let me draw a picture. If R1 is inside R2, the algebra of R1 is inside the algebra of R2. So inclusions go to algebra inclusions, subalgebras. Symmetries. If a symmetry sends the region R to alpha of R, then on the Hilbert space, there exists a unitary or anti-unitary that maps the algebra of R to the algebra of A of R. If we're talking quantum field theory, the symmetry group is the Poincare invariance. So I say these words for Poincare invariance groups, but I don't, this is just local quantum mechanics. I can define for anything, right? This is sometimes called covariance. This is sometimes called isotopy. If you talk to mathematicians, that's what they would say. All right, what else do I need? Spectrum condition. So there is a distinguished operator in the Poincare in this framework I'm talking about. That's called P naught. That's going to be my Hamiltonian. I have an axiom. As an axiom, is that I have the spectrum of P naught better be non-negative. It must be non. This is positive energy condition, positive energy assumption or postulate. It must be assumed. So the fact that it's positive, it suggests that I have a notion of vacuum. That is the state that minimizes this, has zero energy. As a matter of fact, I would like this state to be invariant under all Poincare transformations. This is the uniqueness of a Poincare invariant vacuum, is an, if you wish, possible. What happens if you don't? Well, what happens if this is violated? Can you tell what happens? Let's say your vacuum you found a vacuum that's not invariant under a Poincare transformation. What does that mean? No, it means that you have degenerate vacuum. If my state, right, is vacuum, and I have a U of alpha that commutes with P naught, say rotation, right? If it keeps the energy finite, fixed, unchanged, initially my energy was zero, it means that I have a new state with zero energy. So it means vacuum degeneracy. Right? This is going to be all about what we come next semester to spontaneous symmetry breaking, all of that stories here. So when you have a setup where you have a vacuum, that's not invariant under symmetry. But that symmetry is a symmetry, so it commutes with the Hamiltonian. It keeps your energy conserved, unchanged. You start with the vacuum, you have zero energy, you get a brand new vector, which is still zero energy. You have vacuum degeneracy. Your vacuum is not unique. Oh, it requires a separate analysis. Yeah, well, there's these conditions are a little bit too restrictive in a sense, but we study systems that are more complicated. You need more tools. Okay. Now, what is the Hilbert space? I told you what the prescription is. It says that. Oh, actually, two things. So this is interesting. I define the Hilbert space to be the set of vector space that I obtain by acting with the algebra of R, some finite region, and taking the closure. It must be that this Hilbert space is independent of which region I pick. Otherwise, I can't define Hilbert space. That's one condition. Second, this I have not explained, but we'll come back to this next lecture. There should be no operator, local operator in region R that kills the vacuum. This is probably mysterious. These two combine the fact that the Hilbert space should be generated using the local algebra, independent of R, and there should be no local operator that kills the vacuum. It's called the Riesz-Slitter property together. All right. Good. Sorry, I'm running a little bit behind. Finally, the last thing I'm going to say is causality. If two regions, R1 and R2, do not overlap, and this construction means they're space-like separated, so every operator in R1 must commute with every operator in R2, right? That's causality. And then we write it as the algebra commutes with that algebra. It's causality. Can you guys give me 5 minutes to do the covariant one version? Is that okay? All right, so let's do this covariantly and then I'll pause afterwards. I'm going to describe everything without ever picking a Lorentz ring. Okay? So I'm going to draw pictures in space-time. First thing that causality gives me is this. Start with your space-time. I'm going to draw the pictures in 1+1, but take an open set. There is a notion of space-like separated points to A. It's called the causal complement. It's the set of points, and then we're going to write it as A prime. So every A, there's an A prime. It's not one-to-one. These are the set of all points in space-time that are space-like separated. Can you guess what they are here? These are all the points that are space-like separated. So space-time comes with this operation. It associates canonically to every region a causal complement. Good. Now, an exercise for you guys. Well, a region is called causally complete, so we're going to call a region D. Causally complete if D double prime is equal to D. This region is not causally complete because the prime of it is this. What is the prime of this? The whole thing. Right? So the causal complete region is the enlarging A to this region. A region is called causally complete if it satisfies this. Now, a little exercise for you guys. Every D prime is causal. Every A prime is causally complete. You can prove that. But that's an exercise for you. Okay. So, in the interest of time, let me just give you two sets of causal complete systems and move on. Sets and move on. Half spaces are causal complete. Right? Say there are perpendicular directions. This is a half space. I pick a line. Sorry, I pick a codimension 1 hypercircus in space and shoot null. Right? So this is causal complete. Another region that causal complete is the causal development of the ball. We usually write these kinds of W's and these kinds of T's. Right? Okay. Local quantum field theory is a map from causally complete regions of space, time, to von Neumann algebras. Okay. Where the regions, the causally complete regions of space, time come with the following properties. They come with inclusion. They come with property of symmetry, and then they come with the property of that prime, right? Causal complement. And the map from regions to the von Neumann algebras should respect all theorems. That's what a local quantum field is. So let me just go through that very quickly. First of all, the whole space-time, there's a von Neumann algebra. It's causal complete. There's a von Neumann algebra associated with it. It's called B of H. Right? It's the whole thing. So let's say the set of causal complete regions are D. Okay, local QFT is a map from D to von Neumann algebras of D, such that these three properties are respected. Meaning what? Meaning if D1 is inside D2, then A of D1 is inside A of D2. Symmetry. If there exists an alpha that sends D to alpha of D, then there exists a unitary U of alpha that sends A of D to A of alpha D. Covariance, right? Symmetry. Third, A of D prime is A of D prime. What is prime? The set of operators that commute with A. It's called commutant. This is the shakiest one. Not shaky, there's a long story here. Very, very beautiful story. Okay, but I'm just going to stop here. I'm out of time. This is what a local quantum field theory is. And let me just repeat what the definition is. Given a space-time and a metric, why do you need the metric? To define causal completion. Space-like versus time-like. Given a actually, all I needed was the causal structure. Given a space-time and its causal structure, right? A local quantum field is a map from causally complete regions. Think of that as wedges, half spaces, and ball-shaped regions. Causal developments of ball. Double poles, we call them. To von Neumann algebras that respect inclusion of regions, symmetries of the space-time, the isometries of the metric, which is Poincare in the case of RD 1, causal complement. That's it. And I never said the word field. Any questions? All right, I'm really out of time. And let me just say one thing. So I don't know how useful this was, but